Hi folks, this is the video tutorial for chapter uh, 6 of my textbook, and the title of this chapter is Quenching of a Cylinder. So basically we have a part which is this cylinder, and it's at some high temperature, and we dip it into a liquid, we quench it in a liquid, okay? So because of that, residual stresses will be created that in fact may be so large that drive the part into plastic deformation. So this problem is a combination of a coupled thermal mechanical problem, and because of the fact that it's very long, we can assume that it's in a plane of state of plane strain. But since 3D experience does not have two-dimensional elements, uh, aside from shells, of course, we're going to solve this thing as a 3D problem, but the plane strain condition means that this thing cannot shorten or lengthen. Actually, the strain in the length direction are zero. Now, the things that don't change in this problem are the density and the coefficient of thermal expansion. With respect to room temperature, these are constant, but everything else changes with temperature. I'm not sure whether, yeah, it changes with temperature. So Young's modulus is a function of temperature. Poisson ratio is not, by the way. Yield strength is a function of temperature. Conductivity and the specific heat are also functions of temperature. So basically, we have to do a transient thermal problem and use the information from that transient thermal problem to do the mechanical problem, stress analysis problem. There are some other video segments, but I'm not going to show it to you right now. When we get to them, I will describe it through uh, these tables, these other slides. Okay, so all right, let me put this thing down here for a reference. All right, so we're going to go into 3D Experience. First, I have to log in. Oh, this was already up there, so it's right up there. So I'm going to start with the part design. This will take a couple of minutes. Now, I was going to say that so far I've not I've done only one, I believe, thermomechanical problem, but this is the second one. So let me see now. We're going to start a brand new session. Just give it a minute. My units are already set so that I'm working in SI units, so there's no issue with conversion. The only place that I have a reference to millimeter is this, but of course this is per degree Kelvin, so it doesn't matter if it's millimeter per millimeter or. Okay, we are in business. So let me first of all let me rename these things. So I'll call it properties. I'll call it quenching 2021. and the part or the shape, I'll also call it 3D quenching. Quenching 2021. All right. So on a convenient plane, and for example, on this horizontal plane, I will sketch quarter of a circle and then pad it. So let's draw an arc starting here, 90 degrees. Dimension this thing to be 100 millimeters. Okay, and let's complete the lines from here to here, and another line from there to there, and exit. And we're going to pad this thing by 200 millimeter. Okay, the part is very simple. It's right here. Let us now go and apply our create our material properties. So here we have create a material. Let's call it Quenching 2021. So what it does, it creates a shell for me over here with that name. And what I can do is that I can either apply this thing to my part and then create the numbers there, or I can create the numbers here and then apply it. So I'm going to say simulation, structural, abacus multiphysics. Let's do the density first. The density is that density, let me see for a second, 8442. So that's going to be 8442. Okay. And yeah, the unit is correct. And then we're going to do mechanical, elasticity, elastic, but it's a temperature dependent data, so I will check that box. Notice that I can put the numbers here myself, the Young's modulus versus temperature and Poisson ratio versus temperature, or I can import it. So let me import it. Right click, import. Now I have a folder where these things are stored in it. So let me go to that folder. That data is stored. So desktop, let's write just a second for a second, right there. So I go to 2021, chapter was chapter 6, right? Chapter 6, and quenching data. Okay. So this is Young's modulus, and I have here, and I say OK. Notice that everything is, this is populated here. Okay. So this is fine. And then we're going to go to plasticity, metal plasticity, plastic. And once again, this is temperature data, use temperature dependent data. And instead of me typing these numbers, so let me go ahead and say right click, import. It's in the same folder. That is right here, elastic plastic strain stuff. So it's all populated there. Now, the next thing we want to do is the thermal stuff. So let me see now, where is this thing? Let me scroll down here. Thermal, conductivity. Okay, so you check thermal, conductivity, and make sure you're here, you're not down there, you can't see nothing, so scroll it up. So use temperature dependent data, okay? And this is right click, import, So that is conductivity. It's right here. There is my data here. Specific heat, temperature dependent data. Right click, import. That is specific heat right there. All right, good. Now, the only other thing that's left is the coefficient of thermal expansion. And the ironic thing is that I didn't see the coefficient of thermal expansion up there. It looks like it's somewhere down here under injection molding. I don't know why, but let's see now. Let's scroll down. Scroll down under, what is that, thermal expansion. Let's make sure that you drag this thing up so that you can put the numbers in there. Now that is a constant, and I gave it to you as 1.7 e to the minus 5 per degree Kelvin. So it's going to be 1.7 e to the minus 5. And the reference temperature is the room temperature for that coefficient of thermal expansion, and that is 293 Kelvin. Okay? So I think we took care of everything that we needed here. We say OK, and right click, apply. We are done there. Close that and apply to this part and a check mark. And we can always go check it. It's a good idea. Make sure that we didn't make a mistake. So I'm pretty sure these are all okay. All right. So for example, if you look at conductivity, let's see for a second. Yeah, it's there. The only thing that I want to check is that coefficient of thermal expansion. Now, I didn't do some of these things, but it popped up by itself, but that's okay. Nothing to do with the coefficient of thermal expansion, and this is the number that I put in there, okay? So everything seems to be all right. Now, we are done as far as the part is concerned and the material properties. So what we're going to do is we're now going to go to create a finite element model. So we go there and we go to structural model creation. So 3D Experience immediately meshes this with solid elements. Okay, and you can see that these are the kind of elements that you use if you want to change it. If you want to make it bigger, smaller, the order, you can go there and make changes, or even if you want to make a local mesh refinement, you do it here, but I'm not going to do that, okay? And properties are, of course, created based on the data that are imported. Okay, good. So that's pretty much it as far as this is concerned. So we can go and create our scenario. So let's go to there and structural scenario. The first thing that you do, notice is that you have the choices. You have structural, thermal, or thermal structural. Obviously, it's the last one. And it says that these elements, these finite elements, have not been have not been selected. We understand that. We're going to do that. Okay. Notice that we have thermal and structural, both of them red exclamation marks. So let's start with the thermal one first, okay? So we go to setup. The first thing that we do is select our finite element model. There is really not much to do here. It's just model that was already created. We selected. Notice that this turns green. And if you select the structural model and you do the same thing, you select this, you have to, it will also turn green for structural. So let's go ahead and start with our thermal now. Then we do the procedure. And the procedure is a transient heat transfer step. Transient. This is not steady state. This is transient. Okay. So some numbers that I'm going to put. First of all, I'm going to take 2,000 seconds. Okay. And the time increment, I'm going to use 0.02 seconds. Now, 3D experience will adjust these. If necessary, it makes it bigger, if it's or smaller, okay? And for maximum time increment, I'm going to put 100 seconds. And for the maximum number of iterations or increments, I'm going to put 1,000. And for the maximum temperature change per step, I'm going to put 20K, 20 degrees, okay? And that's pretty much it. So we say, okay, all right. So the next thing that we do is when you do a transient heat transfer problem, you have to specify the initial temperature, right? So thermal. Okay, click on thermal, and where's the initial? Oh, sorry, initial temperature is over here. Initial temperature, and for the initial temperature, first of all, this was uh, basically the slab came out of an oven. It was hot, and I'm assuming that value is 1423. 1423. Okay, 1423 degree Kelvin, and for the support, I'm gonna use meshed part, and this is the mesh that I'm using. I could have also done it from the tree. And I think this is pretty much it as far as that step is concerned. Okay. Then we're going to apply. Incidentally, what I'm going now is to go through some of these slides that you see here. This is what I did, and then I'm going to do the uh, convection boundary condition, or yeah, yeah. So go here. Okay, so for thermal, I have a film uh, convection is right here. You need a film coefficient and the ambient temperature. You click on it. Now let's see what happens here for the support. Again, for the support, the convection is taking place on that face. Okay, and for the film coefficient, this is the film coefficient, another convection coefficient, and it was given here. It was given here as 5910, 5910. So I put down 5910 there, 5910. And the reference temperature, that's the temperature of the fluid, okay? The, the, the fluid that we're going to quench this thing in, and it's 300 degrees Kelvin. 300 degrees Kelvin. And we say, okay, all right. So that takes care of this. All right, now let's move on. And the next step is the next thing that we have to do is to define the step, okay, for thermal, okay. So let me see. Actually, no, we're done here. We're done here. So anything that we haven't specified, assuming that it's insulated, okay. And obviously these planes of symmetry, etc., are insulated, and this is long enough. There's no heat transfer through the length of the cylinder. Okay, so now we're going to switch to structural. Okay, so we go to setup, and we already did this, no problem there. So we have a procedure. It's a static one. Now for the time, I'm going to put 2000 seconds. This is not a dynamic problem, but still it has to be consistent with the time that we gave for heat transfer. Okay. So what else do we have? These other numbers, I changed it to 0.01, 0.01. Oops. You may want to try other numbers, other conditions. Oops. 0.01. Okay, and maximum, I put down 100 seconds. 100 seconds. Okay, and that's pretty much it here. Yep. Yes. And we say okay. Now, for the thermal condition, there's this thing called prescribed temperature. In other words, when I do the static analysis, where do I get my temperatures from? So this defines the temperature. See, that defines the temperature in a region for a structure analysis case. You click on it. Okay, so first of all, as far as the support goes, I can say mesh part, and it's this tetrahedral. Okay. As far as the temperature goes, there's a pull-down menu. It says from the step. Remember, I have a thermostat there. Okay. Automatically, it takes the appropriate thermal step, which was only step 1, and everything else is the same. Everything else is the same, and we say okay. Now, what about the restraints? The restraints, these are planes of symmetry, the top, the bottom, and the sides, okay? So, yeah, and you have to do these separately. This one is a plane of symmetry. This one is a plane of symmetry. That one. And of course, the bottom. Now, the reason the top and the bottom are considered to be planes of symmetry is because we are assuming that, as I said, this is long enough so that there's very little displacement and therefore strain in the vertical direction, and that makes it really effectively a plane of symmetry. Okay, so that's pretty much it. Let me make sure that, yeah, okay, did we forget anything? I don't think so. That's fine. And now we're going to go and, okay, what you want to do is, of course, you're going to run this thing, but later on, we want to plot the temperature as a function of time for a particular location. So I'm going to use this location, for example, this location right there. So in order to do that, we have to create a group. So we go to Model. Under a group, I'm going to select this manual group. Okay, manual group. Now, this is going to pick up nodes, okay, but I can't see my nodes. So let me cancel this. Right-click Visualization Manager management, and then show me the mesh. Well, if you don't get it, just update. Okay, there we are. Okay. Now, so we want a manual group. And I'm going to select this point. Notice that if I select the point over here, any point on this line, if I select this point, for example, it won't move, okay? It won't move at all because the 3 planes of symmetry meet at that location, that point does not. So I'm going to select a different point, maybe this point. I'm going to select this point. How about that? And I say okay. So I have created a group here that a manual group that later on I can use for plotting temperature and displacement of it. Now, I'm sure we are okay. Let's save everything there. All right. We're going to go to our scenario once again. And what we want is, where are we? Scenario. Are we there? Yes. What we want is simulation. But before we run it, we want some data to be collected for that particular manual group, that particular node. So that's over here. You see that? It says output request. Couple of things. I don't want the whole model. I actually want it from a group. And it's that group 1. And I don't want the field information because I want to plot the history of it. So I say history. And there's 2 things I want. I want displacement and temperatures. Okay, so let's see now. If you look at the Displacement is going to give you translation, rotation. We don't have rotations here. And for thermal, I'm going to get nodal temperatures, okay? So we requested that, and we're going to say okay. We save it now. It's a good idea to save these things regularly, because if I have to kill this job, or the communication with the server breaks down, then at least I can always go back and retrieve the last thing that I did. So let's start with model and scenario check. Notice that there's two steps here. You can do these separately, one by one, or you can do it simultaneously. We're going to do that simultaneously. Always pray. Okay. And then we're going to do simulation check. I'm assuming you don't have more than 4 cores, so let's keep it like that. Hopefully no error messages. Warnings, sometimes you can live with it, although it's a good idea to know what those warnings are, because sometimes it helps you to fix the problem if it doesn't run. We'll see. This is not even running it yet. It's just doing a check on the stuff that is needed to do the simulation. Okay. And by the way, what you see here is real time. I did not cut anything. Okay. So, all right. Very good. So close that and finally simulate. Now this one takes a little bit, maybe longer. Okay, so we say fine. In the book, the point that I took by accident, it was the point in that corner that there's no displacement. I get the temperature variation, but for the displacement, I get 0. So that's because it was right at that corner inside of the cylinder on the axis. It doesn't move. But here I selected a different point. I think I selected a different point. Okay, so 10% of the thermal calculation is done. My guess is that this is going to finish in maybe 2 more minutes, because first it does the thermal calculation, stores the temperatures, and then it's going to go and get down to the stress analysis portion. Okay. Although this problem is non-linear because of the, well, first of all, because of the fact that we have plasticity, but it's called a mild nonlinearity. There's no contact stuff there. So the thermal one is done, and now it's going through the structure analysis case. Once this finishes, the first thing we're going to do is look at the stress distribution, temperature distribution, not as a function of time, but at specific time, we get snapshots of the contours, okay? And then at the end, we're going to plot the variation of the temperature of that point, displacement of that point as a function of time, okay? So just be patient, another minute probably. Coming along. You can actually click on the iteration here to see what's going on. It tells you where we are. This is supposed to go to 2000. You can see that initially the steps are very small, but then gradually it gets bigger and bigger, and therefore it won't be very long before we reach the end. My total time was, this is time thing. Total time is, where's the total time? It should be, These are time increments, I believe. Oh, this is the total time, right? It's finished right there. Okay, so let me close this. This is for the uh, structural one, right? Structure analysis. Initially, there is no stress. Let's actually look at the temperature. How about that? So change this thing to temperature, and then we go after the first step, temperature variation here. Remember, the initial temperature was about 1,430 Kelvin. So as we go down, it begins to cool off. Okay, on the outside, the temperature is lower. The temperature of the liquid that we put it in there, I believe, was 300 degrees Fahrenheit. Okay, so you can see that it's going, and after so many seconds, 1,000 seconds, the temperature on the outside is 304, very close to the temperature of the liquid, and inside is hot. Okay, so now, and at the end, after 2,000 seconds, the situation is like this. Okay, now we can go and look at our structure analysis case. Initially, there's zero stress, okay, because it was just hot. It was expanded, free expansion. As we go further, the stresses begin to develop. This is the von Mises stress. And of course, there's plasticity here. And after 2,000 seconds, this is the distribution that you got. So distribution of the von Mises stress. Now, let me go and plot the variation of temperature of that particular point. So you go to plots. You have to go to plots right there, and then you go to XY plot from history. Okay. So first of all, I don't want everything. I want the nodal temperature, and output 3 is where I selected that guy, right, and say apply. There we are. So the temperature initially was there, and it's going to drop, and eventually it's going to go to around, well, I mean, in the steady state situation, it reaches the temperature of the the fluid, which was 300. Okay, so this is pretty much it. Okay, now let's look at the displacement. As I mentioned, when I did the book, I wrote it so that the group that point is taken right at that corner, and therefore nothing moves. But here the situation is different, so let's go ahead and get the displacement translation and the magnitude, and then say apply, and there we are. Okay, so that point begins to move, and of course when it cools down, it shrinks, right? Yeah. All right, that's pretty much it. Good luck, and we can try different things on your own.